Thank you, Sangeeta. Thank you, Praveen sir. So today we'll be talking about the fundamentals of rocketry. I emphasize the word fundamentals because we are not going to talk much about the very complicated equations and very detailed ways in which these systems are designed and operated. We'll be talking fundamentals, the basic principles. We will be discussing what are the principles as I mentioned, then what is the difference between a sounding rocket, a launch vehicle, how a typical mission is conceived and performed and executed. And then we will discuss some basic aspects of satellites, the orbits, etc., etc. Um, so as I mentioned, it's a very basic lecture. And in this picture, the hope this slide is visible. You are seeing an automobile, right? This is the fundamental one of the fundamental modes of transport. And second, hopefully you are seeing an aircraft, and then you are seeing a rocket. So my simple question to you is, what is the fundamental difference between all the three, and is there any commonality? The simple thing, of course, you would have observed is they are basically three different modes of transport. Different as it may look, complicated it may seem, no, from various degrees. If you compare one to the other, fundamentally one commonality is they're all basic forms of transport. A road vehicle may be used to transport oneself from one location to the other, a limited location through the earth. Aircraft can be used for transport for a larger distance through the air, and space. A rocket can be used to transport things from earth to deep space and beyond, right? So this is a very, very common way of saying what are the commonalities and what are the differences. And one thing I would like to mention to you is, no, of course, I know that many of you are science students or with science background. If you take an automobile, let me ask you a very simple question. Who supports the automobile? See, the automobile has got a tendency to fall towards the center of the earth, right? That's what that's we know from the fundamentals of physics, especially the theories concerned with gravitation. So who prevents this automobile from falling towards the center of the earth? The agent which prevents that from happening is the road surface. We have a very firm road surface which provides the sufficient reaction so that the car doesn't fall down. This you please keep in mind. Second thing is how an automobile functions, how an automobile move forward, how an automobile propels itself forward. We have an engine. Inside the engine, we have a combustion chamber where we fill that combustion chamber, or we introduce or spray this combustion chamber with, say, some fuel particles, petrol, diesel, or kerosene, whatever it is. Then this automobile may take air from outside. Air, as you know, is having oxygen, and the oxygen and this fuel will react. You get high temperature, high pressure products. They will be used to rotate a wheel through a series of mechanisms, right? And because of the friction between the wheel and the ground, the car will move forward. So these are the fundamental mechanism by which a car is supported and moving forward. But the same logic, if you apply to an aircraft, who supports the aircraft? Very interesting question. The Earth doesn't support the aircraft because the aircraft is airborne. It is continuously flying through the air. So who supports the aircraft? The same weight of the aircraft is trying to pull it, or rather due to the weight, the earth is trying to pull it towards the center. The aircraft doesn't fall down because the aircraft has got some characteristics in the form of wings and other features by which the air is supporting. The most important point is the air is supporting the aircraft. We will see how it is done and how the aircraft is moving forward. The aircraft is moving forward because that has got a propeller or a jet engine. You take air from the outside and then you burn by the same methods what I have mentioned. The energy is generated. Okay, even though the aircraft is traveling through the air, it has got access to air. It is supported by the air. Now, when you come to rocket, these two principles are not directly applicable, isn't it? For example, the rocket, of course, may be standing on the ground. It may be traveling through the atmosphere, but ultimately a rocket will go out of the atmosphere. It goes to deep space. The other day, Dr. Das has mentioned, about the boundary between the earth, the sky and the space. In the space, whatever we define, you don't have any air particle, or the amount of air particle is too small or too minuscule or too less to have any meaningful use. So you cannot depend on the earth to support the rocket because it's going beyond that. You cannot depend on the air to support the rocket because it's again going beyond that. You cannot expect anything from space to support it. So who has to support a rocket? That's the first question. Second question is, from where it will get the fuel or oxidizer. Fuel, of course, we can carry. It cannot take any oxidizer from outside. So since it is going to a place where there is no fuel and oxidizer, naturally the rocket has to carry both the fuel and the oxidizer. So this is the second difference. So from a scientific point of view, or from a science perspective, you see there are 2 or 3 fundamental differences between these 3 modes of transport. And that is why the rocket technology is supposed to be complicated, because it depends on certain principles which are very difficult to implement. So that is what you call the rocket related technologies. I hope this much is clear from this slide. And now I have just put it in a slightly graphical form as far as an aircraft is concerned. So when an aircraft is in air, when it is airborne, what happens? The weight of the aircraft is trying to pull it down, right? As you're seeing from here. But there is an opposing force provided by the wings. I am not going to the mathematics part of it. You can just only imagine, or you can just you can note that this upward force is called lift, which acts against the weight. And this upward force is proportional to the square of the velocity. The equation is there on the screen for it. You see the lift is directly proportional to the density and the velocity square. So when the aircraft is speeding up, you will get more and more lift. And then there is a thrust, which is a force which propels the aircraft in the forward direction, and all the resistance caused by the air and other dissipative forces together we call a drag. In a normal equilibrium condition, the weight will be balanced by the lift, and the thrust should be sufficient to overcome the drag. So this is how a simple equilibrium condition, or rather the free body diagram of an aircraft looks, right? So the weight will be acting down, the lift will be going up, the thrust will be pushing the aircraft, the drag will try to resist it, but it should be less than that of the thrust. So this is how it works out. Now, as far as a rocket is concerned, the basic principle, everything is same. The thrust has to be upward because the rocket has to go upward. The weight will be acting down. The thrust should be more than that. The drag also has to be compensated by the thrust. Okay, so this is how it may look like. Now, let us just see how a rocket can function in space. See, just imagine you are in vacuum, you are in outer space beyond, say, hundreds of kilometers. You don't have any air, so you cannot make use of anything like a propeller because there is no air to push it against or push it, on a side, or you don't have any solid surface like Earth against which you can again apply reaction or friction. Nothing is possible. So how we can go to space? So there is this gentleman you see on the picture. I hope it's still visible. His name is Konstantin Eduardovich Tsiolkovsky. He was a Russian school teacher. So he has mentioned, or he has postulated in the previous century, I'm not exactly the previous century, in the 19th century, that if ever you have to go to outer space, you have to use a method called reactive propulsion. Let us just see what reactive propulsion is. We all know what reactive propulsion is, but let us just see a simple experiment. It's very clear, right? So in the picture, you can see a person holding a balloon. And as you can see, he is just covering the nozzle of a balloon, the tip of the balloon, so that the entire air at a particular pressure is inside. Just imagine what will happen if he removes his hand or loosens his fingers. What will happen? The air will escape, and then this rocket or this balloon is moving in this direction. This is very intuitive, right? So why it is happening? This reason is very simple. The balloon is having stored air at a slightly higher pressure. So when you release it, when you open it, because of the pressure difference, the air will be coming out. And when the air is coming out, because of the rate of change of momentum, it exerts a reaction. And because of the reaction, it moves in that direction, right? So this is how it functions. So the simple, if you want to go slightly more detail, when you have a closed balloon, you have pressure acting on all the surface of the balloon wall. By a simple way by which physicists used to describe this. And then when you open one side, what happens? Through one side, what happens? The air escapes, so there is no reaction on that side. So the red portion, whatever you see, that becomes an unbalanced force, and because of that, it moves in one direction. The amount of forces, of course, is equal to m dot into v. That's a very simple mathematical way of saying. So here, this particular experiment, you could have understood, if you throw some mass out, okay, at a particular velocity, then you get a reaction. So as I told you, the value of the force may be equal to m dot into v, where m dot may be the mass flow rate, how much amount of mass flows out through every second. So if you throw out a certain quantity of mass at every second at a particular velocity, then you may get a thrust. And because of the thrust, the balloon can move in one direction. Now, the next question is, can the same principle be applied in space? Will it work in space? You may wonder, how it can function. It of course will work in space, because whatever we are discussing here is something is being carried inside and that being thrown off. It doesn't have to do anything with the surrounding. It will work if you are in Earth. It may work if you are in the moon. If it will work if you are in space, and wherever it is, wherever these principles of physics or natural laws of physics or science is applicable, this will work. So you have found out a method which will be functioning not just in Earth, but in also in space. So this is the basic principle of reactive propulsion. Okay, but now the next question is, can you use a balloon to go to space? Of course, it's not possible. Why? The simple reason is you have to have tremendous amount of energy. This kind of small amount of energy provided by the balloon is not sufficient. Let us see another example. Again, a simple example. You have a pot. Assume that it is filled with water, and there are two tubes which are coming out into a kind of a spherical container with two outlets on opposite direction. So you can just imagine, when I suppose if I boil it, the water will be converted into steam. Steam will be coming out, and because of the reaction, it will be rotating. So another way of depicting a reactive propulsion. But can you just say which is more effective? This is more effective because the amount of energy contained in the gas is much higher. Why? Because it is having high temperature and high pressure. Okay, but this is again not sufficient for us, because there is a lot of energy transfer, and because of that multiple energy transfer, there are very large number of losses. Now just see another example. Okay, here you have a chemical. Okay, you have a chemical with both fuel and oxidizer mixed together in the form of a simple chemical rocket, the kind of the one which we generally use for festival purposes, right? So if you light it, it will react, the chemicals will react, and because of the high temperature, high pressure gases produced, it will go in the opposite direction. So here you just compare with the balloon and this. What are the differences? In balloon, it was only storing some gases and being thrown out, right? Not very energy efficient. In fact, not energy efficient at all. Whereas if you see this, in situ high temperature, high pressure gases are produced. That means before the chemical reaction, the amount of space occupied by the gunpowder or black powder or whatever chemical is very small. But as a result of the chemical reaction, huge amount of increase in volume as well as temperature is there. So high pressure will be produced, and because of that, high velocity will be produced. And because of that, this will be going in the opposite direction. So if you want to go to space, you should have a very highly energy efficient, energy producing system, like what you see in this particular picture. Even though this is powerful than the simple balloon, this itself is not very effective as a rocket, because you cannot use any black powder like what we have seen in this picture. But the principle is same. You have to have a fuel, you have to have an oxidizer. When the fuel and oxidizer reacts, high temperature, high pressure will be produced, and this high temperature, high pressure will provide a reaction which can be taking something to orbit or space or wherever it is. So what is the bottom line? You should have a very highly energetic combination of fuel and oxidizer. So this is the fundamentals of rocketry. So the Tsiolkovsky has also postulated famous rocket equation way back in 1903 or so, where he has said the amount of velocity added is equal to BE into the logarithm of mass ratio. You don't have to worry too much about it. Simply it says the more and more velocity added, or rather the velocity added to a rocket is equal to the exhaust velocity created by the jet into the logarithm of the mass fraction. So how much amount of propellant versus how much amount of structural weight or empty weight, that only gives the efficiency of a rocket. So this is, you can, if you are inclined towards physics, you can just try to understand this a little bit more in detail. So the point I'm trying to say is, if you want to go to space, you should have a very highly energetic combination of chemicals which can throw out masses at high velocity, high temperature, etc., etc. So this we will see how it is done. Okay. Now, one important point. If you have just remembered now what I have mentioned, I have told you, if for rocket engines to function, you should have very high force. In one direction, the reaction of the other one will push the rocket upward. So what is basically this force? Mass flow rate into velocity. Or in other words, this entire process of combustion should produce extremely high velocity. Okay, not extremely high pressure, extremely high velocity. So how will you get high velocity? I have mentioned that in all combustion processes, it will produce very high, very large quantity of gases which will result as very large quantity of pressure. But where is the velocity coming in? The velocity is not produced. Suppose if you have a kind of high pressure, no, it doesn't produce any velocity, right? So there is a simple mechanism in a rocket. The system, the basic principle is very simple. It's called a nozzle. Or to be precise, a rocket uses a convergent divergent nozzle. If you see the picture, you can understand this is where the thrust is produced. Then there is a convergent portion, right, where the mouse cursor is coming. There is a convergent portion. There is an area where this convergence, reaches its nadir or zenith, you can say maximum. Then it gets diverged. So you have a nozzle which is having a convergent portion, a point of minimum cross-sectional area. That's what we call the throat. And then we have a divergent portion. So I'm not going into the details of how a convergent divergent nozzle works, but I'm just like to mention that when you have a nozzle like this, the pressure which is produced in the combustion chamber is converted into velocity. Many of you are familiar with the law of conservation of energy. So if pressure energy is coming down, the velocity has to increase, or the potential energy has to increase. So here, assuming that the potential energy is same, if you want to increase the velocity, the pressure has to be reduced, and convergent divergent nozzle is a simple mechanism which affects this. So if you have a combustion chamber and if you attach a convergent divergent nozzle connected to the combustion chamber, all this high pressure in the combustion chamber will be converted into velocity. And typically at the exit of a nozzle, the velocity can be of the order of, say, kilometers per second. Okay, not just meters per second, 3.5 to 4.5 kilometers per second. Whereas just in the combustion chamber, the velocity was 0. So this is one principle you have to keep in mind. So all rocket engine, if you see very carefully, pictures, if you carefully, you will see a nozzle. Many of you would have seen the last Chandran mission or the launch which had taken place last week. So what you see a huge amount of gases coming out at very high velocity. When the rocket is lifting off, also you see large quantity of gases coming out. Why it is getting accelerated? Why it is coming out through very high speed or velocity? Because of the nozzle. Okay. Now I will show two different types of cross sections. Right. Two different types of cross section. So in this cross section, what we are actually showing is two different types of producing the thrust. Okay, so I have just mentioned for a rocket engine to function, what we should have. For a rocket engine to function, we should have a fuel and oxidizer. We have to have a combustion, and as a result of combustion, we should have high temperature and high pressure. So you should have a fuel and an oxidizer. It's very important. In rocket parlance, the fuel and oxidizer are together called propellants. Okay, so it's very cumbersome to say, fuel and oxidizer always, because as far as an automobile is concerned, you only use fuels. You always say it's a petrol engine or a diesel engine. Whereas in rockets, you had to use both fuel and oxidizer. So you don't always say fuel and oxidizer. You just together say propellants. Now, one easy way by which you can do a classification is by the physical state of propellants. If the propellants, that is the fuel and oxidizer, are in solid form, the solid state, you call them as solid propellants. Simple. Similarly, if these propellants are in liquid form, physically, we call it as liquid propellant. As simple as that. Okay, so there is nothing great. It's a very simple way of classifying. So there will be a fuel, there will be an oxidizer, but this fuel and oxidizer will be powdered to very, very fine size. Of the order of, say, microns. 1 micron, if you remember now, 1/1000th of a millimeter. So it will be of the size of microns. They will be mixed together. But if you mix them, it will fall apart, right? So you have to mix them and cast them into a particular shape using a binder. So essentially, a solid propellant system will have a fuel and an oxidizer, which of course are mandatory, then a binder which holds them together. That's what you see in this picture in a brownish form. Okay, and in the core area of the rocket, there will be a empty space kind of thing, which is for the gases to come. And then if I give a start command, you can just see the rocket will be started by a system of units or system of equipments called igniters. And then igniter will allow the entire rockets to catch fire inside, and then all the combustion products produced will be thrown out through the nozzle. And in that process, it will be developing thrust, as you are seeing now. So now what you see, you are basically seeing there is a huge amount of burning taking place in the chamber, inside in the combustion chamber, in the solid rocket interfaces. High pressure, high temperature gases are produced, and the nozzle here is converting that into high velocity. Because of that, you get thrust. In the liquid engine, the principle of rocket thrust production is same, but only one difference is the fuel and oxidizer, they are basically in liquid condition, not just in liquid condition, they are stored in different tanks. You may have an oxidizer somewhere up, you may have a fuel somewhere down. They are in different tanks. Both have to be pumped to the engine separately, and then you have to make them take part in the reaction. Okay, so the basic difference between a solid propulsion system and a liquid propulsion system is the fuel and oxidizers are in liquid form in a liquid engine. They are in solid form in a solid propulsion system. And based on the physical nature or the physical state, they are classified. Okay, this is one way of classification. Now, many of you would have heard many of you would have heard about cryogenic propulsion system. Now, in a liquid engine, as you can see, once the propellants are consumed, the engines will be closed or shut down. Now, you would have also heard about a term called cryogenic engine. So let us just see what a cryogenic engine is in very few, in a couple of sentences or in a few minutes. So, as you know, every engine has got a performance index, right? A simple rough equivalent may be like what you consume, what you save for the mileage. How much kilometers a scooter or an automobile will give you fill 1 liter of petrol. So similarly, here the definition is different, but we use a term called the specific impulse. So specific impulse basically says if I allow a propellant consumption of 1 Newton per meter. I'm sorry, 1 Newton per second. Okay, in terms of mass, in terms of weight, how much thrust I will get. So if you take solid propulsion system, the value you may get maybe 280 to 290 seconds. Some restorable system, one type of liquid propulsion system may give you in the vicinity of 300. Semi-cryo may give something like this. Whereas hydrogen and oxygen combination will give you the maximum specific impulse in the vicinity of 450, 460, etc. So what I'm trying to say is, if you want to find out which is the best combination of fuel and oxidizer, chemically you can understand, because which combination of fuel and oxidizer on reaction produces maximum energy can be found out by chemical energetic. This was also found out by Tsiolkovsky way back in 1903, and he said the best possible combination which can give maximum energy is a combination of hydrogen and fluorine, because fluorine is the most electronegative element. But unfortunately, fluorine cannot be handled. So the next best is oxygen. So if you use a combination of oxygen and hydrogen as the fuel oxidizer combination, you will get the maximum efficiency. Okay, so that's very simple, but there is a major issue. The issue is hydrogen and oxygen both are gases at ambient temperature. Both are gases at ambient temperature. So if we use this hydrogen and oxygen in our propellant tanks, the propellant tanks has to be very, very large because they are in gaseous form. So what you have to do, you have to reduce the volume. So how we can reduce the volume? One simple way of reduction or reducing the volume is to convert the mass liquid. Simple, right? So, but there's a small problem. What is the problem? You are seeing this graph in the middle, and just zoom it, hope it's visible. Okay, so I hope it's still visible, right? So this chart, if you see, you are now at room temperature, maybe at 25, 26 degrees Celsius. Now, suppose if I reduce the temperature to 0, the water will freeze. Okay, we have assumed that we have hydrogen, oxygen, nitrogen, everything around. At 0 degrees, water will freeze. Nothing will happen to hydrogen, oxygen. When you reduce the temperature to say -40, carbon dioxide may get solidified, and you can come to a temperature range below -150 degrees Celsius, which are basically called the cryogenic temperature range. So any temperature range below -150 is called the cryogenic temperature range. So we have crossed -150, we are still going down, but hydrogen and oxygen have not got liquefied. Okay, because their boiling point is so small, so low. And at -193 degrees Celsius, oxygen liquefies. At -253 degrees Celsius, hydrogen liquefies. So what does it mean? It basically says, if you want to use hydrogen and oxygen as rocket engine fuels in liquid form, you have to cool them into extremely low temperature, which we call as the cryogenic temperature range, like -193 and -253 degrees Celsius. So since they are stored in a rocket engine at these extremely low temperatures, they are called the cryogenic engine. We use cryogenic engines because in spite of all these difficulties in cooling, maintaining temperature, etc., we still use cryogenic engine because it gives very good performance. So this is a major challenge you have to take when you are designing cryogenic engine, because as I mentioned, in a cryogenic engine, the liquid oxygen tank, the NOx tank will be at an extremely low temperature of minus 193 degrees Celsius. The hydrogen liquid condition may be at extremely low temperature of minus 250 degrees Celsius, whereas in the engine, just a few centimeters below, will be at a temperature of around 3000 degrees Celsius on the other direction. So everything you have to manage perfectly. You have to have advanced material, you have to have special design and everything. So such engines we are using for our GSLE vehicle in cryogenic engine, and even our LVM3 vehicle, we are using such cryogenic engine. In fact, the vehicle which has sent our Chandran to moon, the LVM3 vehicle also uses a cryogenic engine. So these are some additional info associated with the mode of propulsion systems. Now, we have seen the types of rockets, the rocket stages. Okay, from the fundamentals of the ways in which, the physical state we have mentioned that there are solid engines, there are liquid engines, there are cryogenic engines, etc. So they are basically a combination of fuel, oxidizer, as well as a nozzle. Okay, and a lot of other systems to make the process of taking the fuel and oxidizer into the engine and burning. So everything together, we call it as a propulsion system. So we have just seen what are the fundamental principles of rocketry, what are the different types of propulsion systems based on normal mode of classification. But if you see a launch vehicle, it is different. So what exactly is a launch vehicle? In a launch vehicle, you won't see a solid stage or liquid stage alone. You will see a series of stages mounted one over the other. If you see this particular picture on the right, there are a lot of stages. What you can see, there is a, maybe you can point out from whatever I have just mentioned here. This first stage is a solid propulsion system. The second stage, what you see, is a liquid propulsion stage. The third stage is again a solid, and fourth stage again maybe a liquid or so. What I am trying to say is, what is the ultimate aim for a launch vehicle? The launch vehicle has to launch something to space. That we will see in a little bit detail in the subsequent slides. Now, let me just repeat what I've asked. What is the function of a launch vehicle? We have basically now discussed about the fundamental principle of rocketry, how something can be used with the principle of reactive propulsion, and how the same device can be used to propel something to Earth's orbit or even beyond. Okay, so why you need such systems? For example, how you can make something to orbit there. So this is a very animated view of a very famous diagram, which Sir Isaac Newton himself has illustrated or provided in his Principia Mathematica Philosophiae Naturalis way back in 1672. So what he has tried to show is, just imagine you are on the top of a big, or larger high mountain, and you try to throw something. What will happen? However, say if you throw it with certain velocity, it may go parallel to the earth for some time and it will fall down, right? So suppose if you again use a little bit more force, it may again go back and it may again fall at some other place. So similarly, if we keep on increasing the force, at one point of time, it may again come back to the same position. Or even though it is trying to keep on falling, or by the Earth's velocity, it is trying to keep on falling. The velocity, if you have provided, is good enough, it will overcome that tendency to fall in a very simple terms. So if you try to keep something at high altitude where you are beyond the Earth's surface, then what will happen? It will be keeping on orbiting the Earth. So what I'm trying to say is, if you try to throw something at an altitude with a velocity which is good enough to balance the Earth's attraction, then it will keep on orbiting. Why it is keeping on orbiting? Because there is nothing to prevent it from orbiting. There is no dissipative force. There is no drag. So as indicated by the first law, a body will continue to be in the state of uniform motion unless an external force is supplied. When you are in space, if you are provided with some force, since there are no external force, I'm telling in a very simplified way, there are some forces, but they are too negligible as far as the prime motion is concerned. Because of that, what happens? It will keep on revolving around the Earth. Okay, and if you again give certain higher velocity at a different angle, it can go out of the Earth itself. So the point I'm trying to say is, a satellite will be something which will be orbiting the Earth without any additional mode of energy provision. You provide the energy initially itself. You provide the altitude, you provide the velocity initially. Then if you place it at the right altitude with the right kind of velocity, you will keep on orbiting the Earth. For those who are mathematically inclined or those who are are aware of the physical principle, they will recognize the simple equations I have written on the top. mv square by r is equal to gm by r square. The centrifugal force, or rather the centripetal force provided by the Earth's gravity, gm by r square, is balanced by the centrifugal force provided due to the velocity of the satellite. So if you give a velocity appropriately calculated, it can keep on orbiting there. So that velocity happens to be around 7.9 kilometers per second. So if you provide a satellite with a velocity of typically 7.8 kilometers per second at certain altitude, it will keep on revolving there. So you have got a lot of advantages. Why you have got a lot of advantages? When something is orbiting the Earth without any additional energy, you are only providing the initial velocity, then this rotation is created by that initial velocity only. You don't have to give any other velocity subsequently for years and years, right? So when you have something in orbit, you can use it for a lot of purposes. You can use it for communication. You can use it for remote sensing. You can use it for, scientific studies, so many things. So this is how a satellite basically work. So there are different types of orbit. Just for the sake of completion, let me just say that in the first picture on the left top, you can see the Earth is rotating from the east-west, that west-east, that particular plane, it will be revolving, and the satellite can also revolve in the same direction. So this is what we call a equatorial orbit, because the satellite is revolving around the Earth along the equator, right? And there is another orbit, what you see on the right, which is basically what you call the polar orbit. In a polar orbit, what you basically mean is the satellite is revolving from pole to pole, south pole to north pole, it may be revolving, whereas the Earth will be rotating under it. So you can notice, one advantage of such an orbit is when the satellite is going up and down, the Earth is rotating under it perpendicular to that. So what happens? It can continuously take photograph of the entire Earth because it is rotating around, right? Under it. So that is why the polar orbit is used for remote sensing, that is taking photographs and pictures, etc. There are so many other orbits called inclined orbit, and there are some special orbits called Molniya orbit, which are used by the USSR and by the Russians. We won't go into the details of those. And one point is very interesting. That is what we call the geosynchronous orbit. Geosynchronous orbit is very simple in principle. Suppose if you select an altitude of the satellite is in such a way that the velocity or the angular velocity of the satellite is exactly equal to angular velocity of the Earth. That means the satellite will rotate the Earth once in every 24 hours. So in that case, what may happen? From a particular point on Earth, the satellite may appear stationary. Okay, so this was an idea put forward by Arthur C. Clarke. And if you use 3 satellites, the entire Earth can be covered. And then as far as you are concerned, the satellite may be appearing stationary. So most of the communication satellites are placed in the geostationary satellite at roughly 36,000 kilometers. Okay, so what I am trying to say here is, if you want to have a satellite, the satellite has to be there in space, and satellite should have sufficient amount of velocity. And when the satellite should have sufficient amount of velocity, it means the satellite has to be injected at sufficient amount of velocity. So who does this job? This particular job is done by launch vehicles. So this is the point whatever you have to remember. So one part of our system, one part of the space technology in general is a launch vehicle, the other is a satellite. So these two together constitute the two fundamental aspects of space technology. Now, I think it's clear, no? So we have discussed about the fundamental principles of launch vehicles. We have discussed about the fundamental principle by which a satellite has to be put in orbit. Now, the next question is, who will provide that kind of velocity and altitude, together the energy to put something in orbit? So that job is done by launch vehicles. Launch vehicles. Now, they are very powerful. These launch vehicles are very powerful. They have to be very powerful because this is the kind of energy it has to carry. This is the one question we generally ask, especially children, to have some kind of a comparison. So one LVM3 vehicle, what should be in terms of their weight in terms of elephants? Elephant is a common example. Okay, so the answer is not just 1 or 2. It may be something close to 200 or even more than 200. So you can imagine, when you are having a vehicle, that is the same vehicle which we have used for our Chandran mission. So more than 200 or around 200 times, I mean, an elephant's weight, or it is equivalent to the weight of combined weight of around 200 elephant. You can imagine how much heavy it will be. But the next question is more important. How much should be the rocket? How much should be the power of the rocket to lift something which is having the mass of or weight of around 200 elephant, then accelerate towards moon with these kind of high velocity. So you can imagine what is the kind of power associated with this launch vehicle. So enormous amount of energy and power has to be dissipated by this system. So this is the one point we had to keep in mind. So how a launch vehicle works. So we'll just see that. So I've just taken our PSLV as an example. PSLV is actually a polar satellite launch vehicle. As I mentioned, it's a very powerful vehicle. And if you see very carefully, you can see it has got multiple stages. And if you zoom in, and again you zoom in, many of you may be able to notice the nozzle which I have mentioned. And if you place any one of us in an average high individual, tall individual, he may be only this much high. That means he will not be even at the, he may not be even reaching the end. I mean, he will be, his height will be only less than that of even the divergent portion of a small nozzle. So this is the kind of sizes we are talking about, because if you want to put some payload into orbit, the rocket has to be powerful. The rocket has to have sufficient energy, and the rocket has to have sufficient energy. It should have sufficient quantities of propellant. If it has to encase sufficient quantities of propellant, it should be that much bigger. So that's why the launch vehicles are very, very big. So now let us just see how a typical mission may are planned. And now you know the total velocity to reach orbit is typically around, as I mentioned, 7.8 kilometers per second. Sometimes it can be more if you want to go out of Earth's orbit. So who gives that energy? Launch vehicle gives that energy. The launch vehicle gives the energy all of a sudden within a fraction of a second. Does it give the velocity from 0 to 10 kilometers per second? Absolutely no. Why? If you give that kind of an acceleration, the entire thing will be crushed to a pulp. It's not possible. So you have to keep on adding the velocity gradually. So each and every stage will be adding the velocity gradually from zero relative velocity. It has to keep on adding the velocity till you reach the end. So that is why you have an entire mechanism of small rockets, big rockets, stages, etc. So now we just see the rocket on the launch pad, right? You might have seen when the countdown reaches 0, we say that every systems are ready and the rocket is ready to lift off. We give commands to the rocket starting system. We call the ignition systems. Then it will ignite the rocket's main engine and some of the strap-on engine. The small rockets, what you see on the sides, are called the strap-on rockets because it is strapped onto the main rocket, right? So when you give the command and when the countdown reaches 0, the required engines will be started and the rocket will be lifting off. See, at the point of liftoff, we still have a velocity because of Earth's rotation. That's a very important point. When the Earth is rotating, depending upon your latitude, the Earth itself will give certain velocity to the launch vehicle. So even at liftoff, it has got certain velocity in one direction. Apart from that, when the vehicle is lifting off from a relative velocity to its own position, it is starting from zero velocity, zero altitude, it's going up, right? So what is happening inside the rocket now? It is slowly consuming its propellant, right? It is slowly converting its propellant to high temperature, high pressure gases. And after it's converting into high temperature, high pressure, I'm repeating myself. So it is thrown out through a nozzle with very high velocity. Because of the reaction, it goes up. So what will happen after some time? After some time, what may happen is some of the small rockets, what you see, they will consume all the propellant. So what will you do? You'll just separate it. Why? Because in a launch vehicle, you should not take any unnecessary dead weight because that will be reducing your acceleration. Because what is the total thrust provided by the rocket? Say if it is F, what will be the acceleration to the launch vehicle? F divided by M, right? So smaller is the mass, higher will be the acceleration. Just 1 second. So what I'm trying to say is, if you have this particular rockets, it has consumed all its propellant. What has to be done? It has to be thrown off, right? So that's what we have seen. Similarly, there are 2 more rockets attached to that. 2 more rockets attached to that. Once that is also consumed, that is actually thrown off. So by this particular method of reducing mass, it is accelerating itself. Now, what will happen after some time? the first stage itself will consume all the propellants, right? So that also has to be thrown off, right? So you can see here, even after the first stage, when the first stage is separated, the rocket has reached an altitude of something like 68 kilometers, and around 2 minutes have passed. So significant amount of mass is already thrown off, because that is used only for lifting off and taking it to this acceleration. Then after some time, the heat shield is separated. You know what is the function of a heat shield. Then the same principle which I mentioned will continue. The rockets will continue to fire. The propellant will be consumed, and then once the propellant when it is consumed, that will be thrown out. And throughout this movement, the rocket will be guided in such a way that it is reaching its necessary altitude and attitude. So that they have a system called the navigation, control, and guidance system. And then finally, there is something called a closed loop guidance. So when you understand, when the computer in the rocket understands that it has reached the right altitude, right velocity, orientation, the computer will allow the satellite to be separated in the right orbit. So this is how a particular mission is taking place, right? So from the liftoff to the launch, the separation, everything is controlled by the computer as per the program trajectory. So there is something called a closed loop feedback by which it is done. And a rocket is having, it's a very complicated device with the millions and millions of parts. It has got its own propulsion systems, which provides the basic muscles. The propulsion system is enclosed in a structure that is a mechanical systems. Then it has got its own electronic brain, what we call the onboard computers. They have a lot of sensors. Continuously data will be transferred across during the flight. It will be transferred to the ground for our own understanding. So it is something roughly equivalent to a human system. We have sensory organs, we have our brain, we have our muscles, we have our nervous system. So it's like that. The launch vehicle also has got its own onboard computer, its own individual actuators. The actuators will the system will find out what is the kind of actuation required, and kind of commands will be given to the system. So this way the system will be controlled to its final operation. So this is how a typical launch vehicle functions. So in India, if you see, we have developed a series of launch vehicles right from the SLV-3 1979 to the LVM-3 vehicle. So a lot of things has been done. So now where in the syllabus, you would have also noted, we will discuss something about the history of the launch vehicle or the rocketry. See, way back in the 80,000 or so, the credit of formulating the black powder, which is nothing but a combination of sulfur, saltpeter, and potassium nitrate, has gone to the Chinese. They have made this black powder, and they have used it for the festival purposes, to ward off the evil spirit, and just to create, a lot of fireworks for entertainment purpose. They have used it. The history of, how the technology got spread across the world through, the conquerors like Genghis Khan, etc., etc. And there is an interesting example of the rockets being used in India also in the 1700s, 1790s to 1799, first by Hyder Ali and then his son Tipu Sultan. He has used it against the British in the Srirangapatnam War. So as in the picture, you can see, the rockets were in an iron casing with a lot of, black powder. At the end of the rocket, he used to put some swords or spears, and he used to send it across the enemy. And this used to create a lot of havoc within the enemy area. So this is how these things were done at that particular point of time. And then subsequently, this technology got a huge boost in the 19th and 20th century, because rather than using simple black powder, advanced chemicals were used. And there are pioneers like Tsiolkovsky, Goddard, etc., who has made the pioneering contribution in the beginning of the 20th century. And in this picture, you see what you call the first modern rocket, what you call the V2 rocket, developed by the Germans under the leadership of a German engineer called Dr. Werner von Braun. And then we know the history of the Second World War. After that, we had the Soviet Union putting the first satellite in space called the Sputnik, then the first living organism called Laika. In 1957, we had Yuri Gagarin's flight, then Valentina Tereshkova, Alexei Leonov, and the huge achievement, the crowning glory of the space race in the 60s was the landing of humans on the moon in 1969. because the last, in fact, we are just, July 20th was the launch, and that is celebrated around the world as an International Moon Day. So this is how the history of the space rocket in a nutshell, within a couple of minutes. But what was happening to India? So India, we know, we had great scientists and pioneers in India during this, the freedom time. When we got the independence, we had pioneers like Dr. Vikram Sarabhai, Dr. Homi Bhabha, then Dr. Shanti Swarup Bhatnagar, with the full support of the then Prime Minister Pandit Jawaharlal Nehru. So they started to have a space program in the 50s itself in India, and they wanted to have the space program not just for the credit or glory of saying that we have a space program on par with someone else. They wanted to solve the real problems of our humans, our society, our citizens, our fellow beings who were having, a lot of issues. We are talking about 1950s. India was not a developed country at that particular point of time. There are a lot of issues of communication, information exchange. There are a lot of disasters. You don't have any mechanism to warn people around all those. Everything has started in the 1950s by these great pioneers like Dr. Vikram Sarabhai and Dr. Homi Bhabha. And then one or two points which I would like to mention, which is mentioned in our syllabus, is we had the founding of what we call INCOSPAR, Indian Committee of Space Research, in 1962. As I mentioned, Bhabha, Vikram Sarabhai, they were all the pioneers. And the first sounding rocket was launched from Tumba in 1963, November 21st. You know why Tumba is selected? Because Tumba is very close to the magnetic equator. So you have a particular pattern of charged particles coming from the Earth near the magnetic equator. The way they behave is different from a magnetic poles. Okay, so Dr. Vikram Sarabhai wanted to study that, and for that he had to do some measurements at high altitudes. Okay, maybe 100 kilometers up or 200 kilometers. He wanted to do measurements. So how will you do measurements at 200 kilometers? So you can say an aircraft will go, a conventional aircraft may go up to how much? Even the world record is, that is, if you exclude the record holder, the conventional aircraft will go, passenger aircraft may go roughly 10 kilometers. A Concorde used to go at around 20 kilometers. Military aircraft may go sometimes 30 or 35, but you cannot take any measurements with those kind of systems to hundreds and hundreds of kilometers, right? So what Vikram Sarabhai wanted was, he wanted to use a rocket to take measurements to hundreds and hundreds of kilometers. So one thing you should understand is, unlike the rockets which I have mentioned earlier, these rockets will not go to space and with sufficient amount of velocity so that something can be put into orbit. It's not possible. It will go to very high altitude, maybe 100, 200, even 300, 400 kilometers, but it don't have velocity, but it will go and fall down. But in the process of going up and falling down, or in that process of going up, it can keep on taking a lot of measurements. So this measurement is also called sounding. So those rockets which are used for taking measurements in different layers of atmosphere is generally called the sounding rocket. So that's how the name sounding rocket has come. So ISRO had a series of sounding rockets developed in the 1950s, 60s, etc. The 60s, I mean the 1960s onwards. In the 1960s, first we started by assembling foreign sounding rockets. We never had such a technology, as if you know the history. But subsequently in India, we have started developing our own launch vehicles. I mean, our own sounding rockets. RH-75 was such the first sounding rocket. It was launched in 1967. It had a height of only 1.5 meter. A height of a human being typically, only 8 kg weight, and it could take a payload of only 1 kg to 100 kilometers. Okay, this was the sounding rocket. Whereas an RH-560, that is, RH is basically what we call the Rohini sounding rockets. The RH-560 can go to 550 kilometers. That is, it can be used to take measurements in the ionosphere. It can take a payload of 100 kg, and it is more than 1 ton heavy. So the sounding rockets are basically systems which will go to a few hundreds of kilometers. On the way up, it will keep on doing the measurements, and they will transfer the measurement to the ground. Okay, but it will not stay in orbit, it will just fall down. So this is basically sounding rocket is all about. So India had a series of sounding rocket built, and even today we launch it at a very regular intervals to get upper atmospheric temperature and other measurements, a lot of measurements for the meteorological department. So as I mentioned, first sounding rocket was launched from Tumba in 1969, and this entire TERS area was dedicated to the United Nations in 1968 by the then Prime Minister Srimati Indira Gandhi. You can see in this picture Indira Gandhi dedicating this center with Dr. Vikram Sarabhai and Sri E.M.S. Namboodiripad, who was the Chief Minister of Kerala at that particular time, and Kerala Governor at the time, I think Sri Vishwanathan. So what has been done in 1968 is India has dedicated this facility to United Nations. That means we have opened out this facility for all international collaborations. For example, many of these operated by the United Nations, every country used to come to this place and operate. So this was probably the only place at the time where both the USSR and the Americans used to come and shared the same facility. So there is a great achievement, diplomatic achievements for India at the time also, that such a scientific facility was open to the space superpowers of the world. Not just America and USA and USSR, we had France, we had Japan, we had so many other countries coming in using this facility. So that was a landmark. Then we had the launch of the first satellite, Aryabhata. Aryabhata, as you know, it was a satellite made in India, but at the time we did not have the capability to launch it from India. So it was launched from the former USSR in 1975 using a Cosmos rocket. So that is the first launch vehicle, satellite developed by India. And then we know India has joined the club of nations which had the capability to not just build a satellite, but to launch a satellite from its own technology, its own soil. So this was done in 1980 by a rocket called SLV-3. And this rocket, the project director of this particular rocket, as you're aware, was Dr. APJ Abdul Kalam, who later went on to become one of the most popular president of this nation. So then we had the first Indian in space squadron leader at the time, Rakesh Sharma. He went to space in Russian Soyuz T-11, Soviet Soyuz C-11 aircraft in 1984. Then we had a lot of other major launch vehicles called PSLV in 1994. Then we had GSLV with the first cryogenic experiment. Then we had the spacecraft recovery experiment. We have launched something to space. We have recovered it from space. And we had the Mars orbital mission and the Chandran mission, which of course you are familiar, and I understand there are separate lectures about that. So basically what we do with the launch vehicles are, we can use it for remote sensing. Remote sensing is, as the name suggests, sensing from a remote location. So since this the satellite is continuously revolving around the Earth, you can take photographs. I'm not taking conventional photograph. There are photographs using optical imagery. There are infrared. There are ultraviolet. There are so many different X-rays. There are so many different types of photographing capabilities, followed up by a lot of mathematical modeling, extraction, etc., so that you can get a lot of information out of a picture. It is used for all kinds of purposes, including agriculture, water resources, environment, forest, geoscience, disaster warning, and many, many more. And we had a satellite series called the INSAT series. So INSAT series is International Satellite System, which are basically communication satellite. It is placed at 36,000 kilometers. And then, as I mentioned earlier, since it is at a particular location related to the Earth or India, to be precise, we can use it for communication. You can always see them so that you can always use for communication. And it is also used for disaster warning. Now you are familiar, because nowadays we get very advanced warning about an incoming cyclone, like what you're seeing here. And then with this preemptive information, this preemptive action can be taken with this advanced information, and people can be relocated, and the kind of the damage to the loss, damage to human life is very, very less compared to what used to happen maybe 40, 50 years back, where we are not having such facilities. So this is how the basic technology of launch vehicles and satellites have evolved over a period, and where we are now today. So the time, whatever we have thought to take for this particular class is, I think it's almost over. So I will just summarize, and then we will have some questions. The first thing where we started was by comparing the different types of transportation system, the road transport system, the air transport system, the launch vehicles. What are the fundamental differences? We have touched upon the pioneers like Tsiolkovsky, Goddard. Then we have seen the rocket equation, and then we have seen the different types of propellants: solid propellant, liquid propellant, cryogenic propellant. Then we have seen what are basically cryogenic propulsion systems. Then we have seen how these rockets are used to launch satellites, what is the mechanism by which velocity is added, what are the major subsystems of a rocket, and then what are the different types of launch worm in satellite orbits, and what are the uses of each and every one of them. And then we have seen some typical missions and a very, very small capsule of the world history of launch vehicle developments. And we have seen how India had started our launch vehicle space program, and how it has evolved over a period of time, and what are the basic technologies today we may possess. So with this, I think we have just reached the time now. The lecture was between 3 to 4. We have reached 4 o'clock, and if Sangeeta has got any questions collected, we will